Hello and welcome back to the channel, and today's topic is something I'm pretty passionate about, which is rhythm games. I've made 4 so far and I intend on making more, and let me share what I've learned so far. We'll start out by talking about a custom controller node that can be extremely useful and central to almost any kind of rhythm game out there, and then we'll see how we can use it to make a simple Guitar Hero clone. The custom control node we'll be talking about is called the Conductor. One of the first questions you ask yourself when you start making a rhythm game is, how do you match events in the game to the beat? And this is the problem we'll be tackling by making this node. Let's delve into some quick theory first. When we're making a rhythm game, we generally have a song that we're working with that has a certain BPM. The BPM is very useful for us because the game feels most natural when events in the game happen on the beat of the song. A variable that we can figure out from the BPM is the seconds per beat. This variable is useful to us because events in the game happen in seconds and we want to convert that into beats. Another thing that we might want to consider are measures, and measures are important because a lot of the patterns in songs are repeated over these measures. We could have a drum on the first measure, a kick on the second measure, and etc. A song could have more than 4 measures. It could have 8 or it could have less, but in this case we'll be working with a song that has 4. And we can use measures in order to make sure that similar events happen on first measure, every second measure, every third, and every fourth measures. And the way that measures work is we have a beat. First beat, second beat, third beat. If a song has 4 measures, the first beat will be the first measure, second measure, third measure, fourth measure, and then it goes back to the first. So now that we've covered how songs work broadly, we are going to talk about what exactly we want from our conductor class. We want to be able to track which measure we are on, and in Guitar Hero's case, it just means that we want to be able to spawn 2 arrows on the first measure or 1 arrow on the third measure. We also want to be able to track which beat we are on, and the reason why we need both is because we can use beats to switch up what we spawn on each measure. So in song transitions, what happens on each measure changes. So there could be a song transition on the 50th beat and another song transition on the 100th beat, and etc. Beyond this, our conductor node will be able to sync to the exact song position. And the reason why this is important, in Godot you might have the idea to use timers in order to track the beats in your song. However, there are some intricacies as to how exactly the audio is processed in output, which makes the system clock, which is what Godot timers run on, not a very viable option for tracking the position of the song accurately. You can read more about this in this Sync the Gameplay with Audio and Music article in the Godot documentation, but essentially what's important for us here is that in the long run, the sound hardware clock is never exactly in sync with the system clock, and the timing information will slowly drift away. That is the first point. And the second point is that mixed chunks of audio are not played immediately, and audio stream player play sound will not begin immediately, but when the audio thread processes the next chunk. So oftentimes the audio is not actually output exactly when we think it will be output. Sometimes there are delays in when it starts playing, and after it starts playing, it slowly starts drifting off. So all of this can have negative effects on how synced our gameplay is to our music, and that's what we want to avoid. So now that we know what we want our conductor node to do, let's see how we'll go about implementing it. The first thing that we'll focus on is how we'll be keeping track of the song position from which we can figure out which beat we are on currently. So the recommended way to do this is to set the time to player, which is the audio stream player, get playback position, which returns the song position in seconds, plus audio server get time since last mix,
and minus audio server get output latency. This seems like a lot, but I will explain how this will work. The first thing we're calling is audio stream player. This will return the position of the song in seconds. And it would seem that this would be enough for us. However, what get playback position actually returns is the last updated playback position. And it's not updated every frame of our game. So let's say we are running through 8 frames of a game. We are asking for the get playback position every frame, and what's reported is 0.0 seconds at the first frame, 0.0 seconds at the second frame, 0.0 seconds at the third frame, and on the fourth frame it's updated to 0.06, and then fifth frame 0.06, 0.06. So this is how an output of get playback position could look. And we want to push it to be slightly more accurate. And the way that we do that is by getting audio server get time since last mix. And what get time since last mix does is it reports the time that has passed since the last playback position was reported. So it would be 0.0. On the second frame it would be 0.02. The third frame it would be 0.04, and on the fourth frame it would be 0.0 again, because we reported the playback position and the time is reset to 0. So both of these, when we add both of them, we can have a very accurate representation where we are in the song currently. When we add both of these up, we will get 0.0, 0.02, 0.04, 0.06, and so on. The last thing that we see there is audio server get output latency, and we subtract that from our time. And what it does is it gives us how long it takes for the audio to be output to the player since Godot has sent it to be output. And this basically just offsets the delay that the person playing that game would get between our game thinking that he's hearing the song and him actually hearing it. Now finally, let's take a look at the implementation of the Conductor Node. The Conductor Node is an audio stream player. It's an extension of the audio stream player. It has 2 custom signals, beat, which reports the song position and beats on every beat, and a measure signal, which reports the measure of the song on every beat. There are a couple export variables that allow us to use the Conductor Node with any song we want to play. It's BPM and measures, so we can go into our game scene and go into the Conductor Node, and we can set custom measures and BPMs. We have our song position, beats, and seconds per beat variables. A second per beat variable is, like I said, 60 divided by BPM. On every physics process, if the song is playing, we get the song position, like outlined earlier. We get the playback position from the audio stream player, and then get the time since last mix from the audio server, and then subtract output latency from that. We figure out song position and beats by getting song position divided by seconds per beat and getting the 4 of that. So basically here, by 4ing it, we're getting the last beat that we already passed. And since a beat is an integer, we just cast it to an int. This I will explain slightly later, but now let's look at our report beat function. If last reported beat is less than song position and beats, we don't want to keep reporting our beats. So if we already reported it, we just save it in our last reported beat and not report it again. Here we make sure that our measure resets once it reaches this number, and then we emit signal beat and song position and beats, and then we emit signal measure and the measure. We set the last reported beat to song position and beats and increment the measure. And with these 2 simple functions, we have already achieved a lot of the things that we wanted to do already. There are a couple other functions here that make our life way easier, and I'll show them to you now. The first one is play with beat offset. So let's look at the game real quick. As you can see, we start spawning the arrows before the song actually starts. And the way we achieve that is by having this function. We queue a couple of fake beats, so we'll report a couple of fake beats before the song actually starts. So our game node is able to spawn those arrows on those beats. So we set beats before start equals num, set the wait time to seconds per beat. So we're actually using a timer here to track the beats before the song actually starts. So this timer will basically measure out an amount of beats that we pass to it. So let's say that we want to start spawning 8 beats before the song starts. We pass it 8. And a quick note before we go into how this timer works. I actually made a mistake in the original implementation. This if statement was originally song position in beats is less than beats before start. However, this if statement is never reached if that's the case. So we want to make sure that it's beats before start minus 1. And this timer will measure out 8 beats before actually starting the song. We report the beat on every timeout of this timer. Since it's a one-shot timer, if the song position is in beats is less than beats before start, we just restart the timer. However, what's important here is if song position in beats is equal to beats before start minus 1. So basically on the last beat before starting the actual song, we measure slightly less time than we're supposed to. What we measure here is the normal wait time, so seconds per beat, minus audio server get time to next mix. And what audio server get time to next mix does is it tells us what the delay is going to be before our audio stream player can start playing the song. As mentioned before, if you call audio stream player play, sound will not begin immediately, but when the audio thread processes the next chunk. This delay can't be avoided, but can be estimated by calling audio server get time to next mix. And this is what we're using here. Since we want the wait time to be seconds per beat, we have to account for the amount of time that it will take for the audio stream player to actually start playing the song. So that's why we're subtracting this and this. After that, once it reaches beats before start, we just play the song and stop the timer and go back to our normal physics process. And in our physics process, we actually add beats before start to song position in beats. The last function here is more of a convenience than actual functionality, but it allows us to start a song from a specific beat. So when we're creating a level, for example, we don't have to start it from the beginning. We could just go to a specific place. So we could go to the end of the level. We could go to the middle of the level. And etc. So we start, first of all, we start playing the song and fast forward our song to the position beat times seconds per beat. And then we set beats before start to offset so that we can continue doing this. And the last thing that we do here is count which measure we'll land on after doing this. So we set a new variable I. And while I is less than beats before start, we keep incrementing measure, resetting it to 1 once it reaches measures. And increment it. I just realized that we don't actually need to do this while loop. Oh my god. Okay, anyways, we set measure equals beat modulo 4 yep, exactly the same. Interesting. Not sure what I was thinking. Anyways, now let's see how this conductor node will allow us to create an actual rhythm game. So let's look at our setup here. We have our arrow buttons, which you can see at the bottom. They are animated sprites, which we switch from this one to this one once we click their respective actions. We have 3 areas, perfect area, good area, and okay area, which allows us to track where the note arrows are wending. And we have an export variable input, so in which we basically just put which input action we want this arrow to represent. We have 3 variables, perfect, good, and okay. We have a variable for current note, which starts out at null. Once a note, which is just one of these, lands inside our okay area entered, areas in group note, okay is true, and current note is area. Once it goes down further, it enters our good area. It will set good to true. Once it goes down further, it will enter our perfect area. We'll set perfect to true. And once it starts exiting them, we'll set perfect to false, good to false, and then okay to false, and then current note. If event is action pressed, and echo is false, so if the action was just pressed, which is just this input that we set in our inspector, and if the current note is not null, we get parent increment score by 3 and destroy the current note with a score multiplier of 3, which just tells it what kind of label to send out. It will send out a perfect label, a good label that says good, or a label that says okay. If good, increment score by 2, do the same thing. If okay, increment score by 1, and destroy. Reset. What reset does is sets the current note to null and resets all of our tracker booleans. Otherwise, if current note is null, we get parent and increment score by 0. And what increment score does is if it's more than 0, it increments our combo, and otherwise it sets our combo to 0. So that's why we're actually sending increment score, so that we can reset the game combo. And if it is pressed, we just set the frame to 1, which is this. And if it's released, we start a timer, which will keep in this frame for 0.05 seconds. It's very minor. So let's look at the note real quick. We have our target y and spawn y variables. Target y is just the position of these on the y-axis, and spawn y is where we're spawning this node. And we have 3 spawns: left way in spawn, center way in spawn, and right way in spawn. We set our speed to 0 initially, but on initial lines, when we pass a lane that this node will be in, we first of all set its position, set the frame of it. So there's 3 frames: left, top, and right, and we set the speed to distance to target divided by 2, so it will take 2 seconds for this node to reach our arrow button. Once we destroy it, we emit some particles, set animated sprite visible to false, start our death timer, which will just count out how long until we want to queue free this, because we want to give time to our CPU particles and our label to appear to the player. And we set our label, which didn't have anything before, to either great, good, or okay, depending on the score that we sent from our arrow button node. In the physics process, we just move our position down by speed times delta. Pretty standard, and if we pass 200, we reset the combo. This means we missed the note. 200 is 20 pixels below the bottom of the screen, and otherwise, if we're not hit, if the note was not hit by the arrow button yet, we do this, and otherwise we move the position of the node which holds our weighable. We need to put a weighable. We need to put the weighable inside the node because our weighable doesn't have a transform variable, so we can't set its position. We can only set its extents, and it's just way easier to set the transform of the node instead of moving the weighable in a weird way. So with all of this in mind, we have our game. The way that we track how many arrows to spawn on every measure, so this is first measure, second measure, third measure, fourth measure, we set these variables. So we'll spawn 0 nodes on the first measure, 0 on the second, 1 on the third. And we change this depending on the song position and beats from our conductor node beat. So this sends out a beat signal, and once that reaches more than this, we change up how many notes we spawn. Once it reaches this, we change up how many notes we spawn on each measure again, and on every conductor measure signal, we spawn this amount of notes over here. So if measure is 1, we spawn. If measure is 2, we spawn this amount of notes. Measure is 3, we spawn this amount of notes. Measure is 4, we spawn this amount of notes. The way we spawn notes, so this function is a bit of a hack. If we're spawning more than 0 notes, get a random Wayne, instance a note, initialize it with its Wayne, and add child. If we're spawning more than 1, which means we're spawning 2, these are the only 2 options. We're either spawning 0, 1, or 2 notes, while our random number is equal to Wayne, so this. So it's the previous Wayne that we spawned. So we don't want to have 2 nodes on the same Wayne. We set random to a random number from 0 to 2. And then if it's not the same Wayne, we set Wayne to random instance, node instance initialize Wayne, and add child instance. Pretty simple. There are a couple minor things we didn't cover here, like scoring and the end screen, but I will link to the GitHub project in the description. You can download it and look at it if you'd like. So this concludes our tutorial. Hopefully you can see how creating a custom conductor node can be useful in your rhythm game. This video was heavily inspired by a Gamasutra article, Coding to the Beat. I'll link to that in the description, as well as some other relevant readings and this project on GitHub. Hopefully I didn't go too fast in some of the parts, but if you have any questions, please let me know in the comments. Thank you for watching and have a good day.